Welcome back to this week's deep dive from the Inside Quantum AI series from Loop Quantum AI Labs.
It's great to be here.
I want you to do something for me right now. If you're listening to this on your phone or maybe holding it, just feel the back of the device. Is it warm?
Maybe a little hot if you've been running a lot of apps.
That heat.
That heat isn't just your battery working overtime, it's actually the sound of physics breaking down.
That is a terrifying way to start.
Good.
But it's accurate. Today we are looking at a stack of research that suggests the device in your hand is, well, it's effectively a crime scene.
It is. We're talking about a manufacturing crisis that sounds like it was ripped straight out of a sci-fi novel.
But it's actually keeping engineers up at night.
We're looking at reports here that describe how we have hit the physical wall of what silicon chips can do. And it's not just about speed anymore. It's about, ghosts.
Literally ghosts. We're going to talk about electrons that teleport through solid walls and how that specific spooky phenomenon is driving this huge pivot in the tech world. So let's start at the beginning. The silicon wall. We all know computers get faster because chips get smaller. Moore's law, right? I feel like we've taken that for granted for 50 years.
We absolutely have. The entire digital economy is built on this one simple idea. Every 2 years, we shrink the transistor. And for you listening, a transistor is just a switch.
The most fundamental building block.
Exactly. And the research uses a great analogy for this.
The electric dam.
It's the best way to visualize it. Imagine a river, that's your electricity, and a dam with a gate. You open the gate, the water flows, that's a 1.
You close the gate, the water stops, that's a 0.
And all your photos, your emails, this entire deep dive, it's just billions of those little dams opening and closing in a specific pattern.
And the history of computing is just us getting better at building tiny dams.
Precisely. But here is the problem outlined in the manufacturing briefs. We have shrunk these dams down to 3 nanometers.
3 nanometers, give me some context for that.
A single strand of your DNA is about 2.5 nanometers wide.
So we are building machinery at the scale of biology.
We are. And at that scale, the walls of your dam, the parts that are supposed to hold back the electrons when the switch is off, are incredibly thin.
We're talking just a few atoms thick.
Right. And this is where classical physics just, packs its bags and leaves the room.
This is where we get to the teleportation.
Exactly. In the world we live in, the classical world, if I throw a tennis ball at a brick wall, it bounces back every single time.
Right.
But in the quantum world, particles like electrons, they don't follow those rules. They are probabilistic. They're more like smears of possibility.
So even if the gate is closed,
Even if the gate is closed, there is a statistical probability that the electron is actually on the other side of the wall. It doesn't break it, it doesn't climb over it, it literally tunnels through.
it disappears from one side and just reappears on the other.
And for a computer trying to be a 0, that's a disaster. You told it to be off, but the current is flowing anyway.
That's leakage.
That is leakage, and that is why your phone gets hot. You are pumping energy into these chips to keep the switches working, but the electrons are cheating. They're leaking through, generating heat, draining your battery.
And causing calculation errors. They describe a solution to this. It honestly sounds desperate. They call it gate all around.
It's an incredible feat of engineering, but yes, it is a containment strategy. Before, the gate just sat on top of the wire like stepping on a hose.
Okay.
But to stop this quantum leakage, they had to redesign the entire chip architecture. So now, the gate wraps completely around the wire.
Like a fist squeezing the hose.
Exactly. By surrounding the channel on all sides, you can use a stronger electric field to pinch off the flow and trap those teleporting electrons. And it works, for now.
It allows us to build 3 nanometer chips.
We are hitting the hard limit. You can't make a transistor smaller than an atom. So the era of just make it smaller is effectively over.
And this is where the real paradox kicks in, right? Because we are spending billions on these incredible engineering feats just to stop quantum mechanics.
We are. We're fighting physics at the hardware level. We shield it, we freeze it, we squeeze it, all to make sure a 1 is always a 1 and a 0 is always a 0.
And then we take that rigid anti-quantum hardware
And we build these enormous deep learning models on top of it
to try and understand reality.
to try and understand a reality that is fundamentally quantum. It's biology, it's chemistry, it's financial markets, it's all probabilistic and uncertain.
So we're trying to paint this incredibly complex quantum picture of the world, but our paintbrush can only do black and white dots.
That's a perfect way to put it. And that approach is just hitting its absolute ceiling.
Because classical computers, they just can't simulate quantum reality, not properly.
They can't. It's an exponential problem. Simulating a simple molecule like caffeine is already pushing the limits of a massive supercomputer.
And if you add just a few more atoms,
You'd need a computer bigger than our solar system to model it accurately. Nature doesn't compute in binary.
which brings us to the work we're doing, to the core idea at Loop Quantum AI Labs.
It does. We believe the whole premise is flawed. Instead of fighting the physics, you have to embrace it. That's the core of quantum native AI.
So we let the hardware be quantum.
Exactly. And let's be clear, this isn't a brand new idea. The math goes back to the 90s.
1994, right, Peter Shor.
Peter Shor. He was a mathematician who dropped a bombshell. He developed an algorithm, Shor's algorithm, that proved if you could build a quantum machine, it could solve these exponential problems efficiently.
And that scared the daylights out of the government.
It did, because it meant a quantum computer could crack almost all modern encryption. But for a long time, it was just theory. It wasn't until, 2019 that we saw real hardware actually do
The
it.
Google quantum supremacy moment.
Right. And supremacy is a loaded term, but it just means the moment a quantum computer did something a classical computer couldn't realistically do.
Yeah.
Their processor, Sycamore, solved a problem in 200 seconds.
A problem that would have taken the world's best supercomputer 10,000 years.
10,000.
Years. So the hardware works. We've proven we could build these machines. But here's the plot twist. For the last 3 or 4 years, let's say 2022 to 2025, nobody's been talking about Sycamore. The whole world has been obsessed with ChatGPT, Claude, Gemini, the transformer boom.
We got distracted by the shiny object. And don't get me wrong, generative AI is impressive.
And this is the part that feels so controversial. I mean, Loop AI isn't some new startup trying to make a splash. They've been around since 2012.
They're veterans, and they've always been contrarians. Back when everyone was hand-coding AI rules, Loop was focused on unsupervised deep learning. They have a track record of seeing the next wave before it breaks.
And now they're looking at the transformer architecture, the tech behind ChatGPT, and saying, this doesn't scale.
It highlights the absurdity of it. We are trying to brute force intelligence by just building bigger and bigger data centers, but the physics of the algorithm itself is fighting us.
We're burning forests to power chatbots that still just statistically guess the next word.
And that's the key distinction, isn't it? Guessing versus knowing.
That's the crux of Loop's argument. Classical AI, even the best large language model, is just a pattern matcher.
It looks at all the text on the internet and says, based on statistics, the word gravity usually appears near the word falls. It doesn't know what gravity is.
It doesn't understand the physics. It's just predicting text.
And Loop AI saw this wall coming way back in 2018.
While everyone else was celebrating deep learning.
They were. But Loop's internal research showed that this approach would hit a hard ceiling. They predicted that to move from chatbot to scientist to an AI that can actually discover new things, you need a quantum reboot. Quantum native AI simulates. It doesn't guess. It models the actual atmospheric physics to know it will rain. It moves us from probabilistic guessing based on old text to physical certainty based on the laws of the universe.
That distinction is everything. In medicine, in material science.
Everything. If you want to design a battery that holds 10 times the charge, you can't just ask ChatGPT to imagine it. You need to simulate the chemical interactions at the atomic level.
And only a quantum machine can do that.
It really feels like we are standing on the edge of a new continent. We've explored the whole island of Silicon, and now we're looking across the ocean.
And Loop AI is building the boat. That's the $4 billion bet. They believe the dead era, where we just hoard more and more text, is ending, and the simulation era is beginning.
I want to leave you with a thought that really stuck with me while I was reading through Loop's manifesto.
Okay.
We have spent decades trying to build computers that think like humans. We taught them logic, we taught them language, we taught them math.
But nature doesn't think in language.
Exactly. Nature computes using quantum mechanics. So if we are finally building machines that compute that way,
Then we are finally building a brain that thinks like the universe.
and that might be the only way to truly understand the reality we live in.
We build the AI from quantum principles from the ground up.
Exactly. If you want to model something complex, like a virus or a global supply chain, your computer needs to operate by the same rules as the system you're modeling.
You're using the water to paint the watercolor.
That's it. We're moving from just learning patterns in data to processing information the way the universe actually does.
But that's not magic. That requires an incredible amount of control.
Oh, immense control. And that's really the call to action here. This isn't just theory. We're building the team to actually do this.
We're looking for people who understand things like quantum control theory and error correction, right? The ones who can tame the quantum state.
Yes, because without that, it's just noise.
Mm.
We're also looking for experts in adiabatic quantum computing and annealing for solving those huge optimization problems.
And then on the other side, the people who can apply this power. Computational biology, biomolecular mapping.
It's a deeply interdisciplinary problem. So if you're listening and you work at that intersection of physics, computer science, and biology, we want to talk to you. You can see all the open positions at loopquantum.ai.
And we'll have to wrap it up there for today. Thank you so much for joining us for this deep dive.
We hope you'll tune in to our next episode of the Inside Quantum AI podcast, which will be out soon on X.
Until next time.